PowerPoint. Okay, so hi everyone. It's my pleasure to have this chance to give you this talk. So my topic will be the upland spins induced unconventional perpendicular magnetization switching behavior. I'm Liu Yakun from National University of Singapore. So we know that the spin orbital gate-driven magnetization switching could be used to create efficient spintronics memory devices. So, however, the switching mechanism have its intrinsic limitation. For example, so for the conventional heavy metal and ferromagnetic bilayers, an external magnetic field is necessarily applied to be collinearly parallel to the current direction. Only in this way, the PMA switching can be realized. So in recent years, the researchers have employed many methods such as interlayer and exchange coupling, and also the structural engineering and many methods to overcome this limitation. However, all of them requires complicated device verification process or requires an additional magnetic layer, which reduces the storage density and the device endurance. The outland spin, or we call it the Z damping like torque, and it offers a more efficient approach. In this case, the outland damping like torque directly counteracts with the magnetic damping, and the switching of PMA ferromagnetic materials can be achieved at zero field. Meanwhile, this is a very low power consumption switching method. We can see from this figure, this is a theoretical calculation. We can see that the switching accomplished by the Z-damping like torque has a very low current density requirement compared to the conventional heavy metal and ferromagnetic layer like this, where the external magnetic field is also required. So in practical application, the upland damping like torque can be easily exerted by the upland spins, or we call it the Z spins. Methods like the spin precession, magnetic spin Hall effect, low symmetry material have been proposed. Among them, using the low symmetry material, such as the wheel semi-metals, can be the easiest one. So we can see that with the absence of twofold rotational symmetry, the Z spin can be generated and observed. So following the observation of the Z-spin polarized current generated in the tungsten ditelluride, a wheel semi-metal, very famous wheel semi-metal, the field-free switching of PMA can be realized and using WT2 and the spin source at low temperature. Note that this is at the low temperature. This temperature is imposed by the PM layer. So we know that for the commercial use application, we always require the room temperature. And also the WT2 has very low spin Hall conductivity. Meanwhile, from the mechanism, we also have no idea about the detailed speed dynamics of the field switching and also the role of the Z spins in this switching process. So this is also the main topic of our work. So in our work, we explored the titanium iridium telluride, or the TRT4, as the spin source. So as a ternary type 2 wheel semi-metal, this material has the substantial spin overcoupling, and also has, which is potentially for the high spin Hall conductivity, and also it can, with the absence of twofold rotational symmetry, can be a candidate for the Z-spin generation. Meanwhile, it has very high charge conductivity compared with WT2 and MOT2. We can see here, this is a number, this is twice, or the third times. Then, in our work, we firstly examine the outland damping like torque using STFMR methods. We can see that here, the amplitude difference in the asymmetry parts, the red color part, indicates the existence of the upland damping like torque induced by the upland spins. So following the established analysis method, the spin Hall conductivity of this material has been estimated in the order of 4. So this is almost 1 order than the WT2 and other TMD. We can see that our work is marked by the red area, while the other TMDs, including the WT, is here. The x-axis is the Y spin Hall conductivity, while the z-axis is the there is a table. So the x-axis is the Y spin Hall conductivity, while the y-axis is the Z spin Hall conductivity. The more on the right and the higher indicates the better the Y and Z spin Hall conductivity. We can see that our is almost this is much better. So in other words, compared with other platinum and topological insulator, this material has a higher has substantial Y spin Hall conductivity and also the Z spin Hall conductivity. This is potentially very good candidate for the field free switching with low power consumption. Then, based on this conclusion, we performed the room temperature current-driven perpendicular magnetization switching by using the Hall bar devices. This is our structure. We use a commercial PMA structure with the cobalt iron boron with the titanium buffer layer. So we can see that the square shape of this HE loop in the fabricated devices indicates the PMA is well maintained in our measurement and after the fabrication, which is consistent with our expectation. Then, by applying with larger current of plus and minus 5.7 milliampere, we can see that a clear loop shift. We can see this is the red line is shifted to the right, while the black line is shifted to the left. This is called the HE loop shift. The existence of this loop shift indicates the existence of this beam in our measurement. So on the contrast, when the current is flowing along the B axis, there is no loop shift at all. You can see that the red and the black line, they almost overlapped. Okay, so well, based on, we know that this loop shift is generated by this beam. So we also try to extract the this beam Hall angle. I mean, which is also can be understand the efficiency of this beam generation. We can obtain this number, which is similar to the number obtained from our STFMR measurement, which is measured by an in-plane magnetic by the spin of torque generated in in-plane magnetics, the FM layer. Then we demonstrated the SOT induced magnetization switching with current pulses and room temperature. So here we can see that under zero magnetic field, a clear magnetization switching of the PMA cobalt boron layer can be accomplished. The critical current density is estimated around 7 multiplied 10 to 6 ampere per centimeter square. Meanwhile, we also noted that the switching polarity doesn't change with the external magnetic field direction change. This is very abnormal. This absence of polarity change can be repeated in different devices. So we know that in the conventional in-plane spin generated induced SOT switching mechanism, for example, in the heavy metal and the PMA structure. So the switching polarity will be reversed while the opposite while the external magnetic field direction is reversed. So but in our case, with the external magnetic field direction sign reversal, the switching polarity keeps. So we expect there is some relationship with these beings. Based on this hypothesis, we performed a numerical calculation based on the microspin model. So we can see that the result is also well repeated in our simulation. So with the sign reversal of the external magnetic field, the switching polarity keeps. Meanwhile, we also explored the trajectory. It's very clear that the switching process is accomplished through the anti-damping process, which means that the Z-spin dominates the switching. So in this case, we can conclude that the Z-spin dominates this switching process and also dominates the switching polarity. So here I will give a short summary. So we know that we have in this work we explored the TRT for spin Hall conductivity, which has very high spin Hall conductivity, it's around 1 order larger than WT2. And then based on this material, we realized the field-free PME switching at room temperature with the critical current in the order of 10 to 6 ampere per centimeter square. Then, most importantly, we also note that the change of switching polarity is absent with external magnetic field sign reversal. Meanwhile, we also know from our simulation, we know that the Z-spin dominates the switching process. So our results provide a pathway to utilize tele4 for the scalability and stability for the spintronic devices. The above works has been accepted in Nature Electronics and now in price. So that's all. Thank you.
Thank you so much. Is there any? Okay, this is our only question. Yes, please.
Do you hear me?
Yes.
Okay, thank you for very interesting presentation. I'm interested in the material, tantalum iridium telluride. From your group, also you measured the nonlinear Hall effect of this material, and you found that sign switch between room temperature and low temperature. So do you also find this kind of sign switching behavior in spin Hall conductivity in your experiment?
In my experiment, I mostly explored the room temperature switching and also the room temperature, the spin SOT, because our aim is for the room temperature commercial application. But for your question regarding the low temperature application, so I think this I noticed the charge carrier change and low temperature. So, but I'm not sure whether this will also change in the low temperature. Maybe this will be the future topic.
Okay.